Hello, the purpose of this video is to prove to you some of the identities that we learned in class, the sum and difference identities. And these have to do with if you have, say, the sine of a sum of two angles, or the sine of a difference of two angles, or the cosine of a sum of two angles, or the cosine of a difference, etc., or tangent as well. And we have formulas for those that we learned in class, but we didn't prove those formulas in class, and it's always nice to see the proof so you don't think that the formula just fell out of the sky and that it's some magic trick. Okay, so here we go. What you see that I've drawn is an angle alpha in standard position and an angle beta in standard position, and I just chose to make alpha greater than beta, but it doesn't really matter. It just simplifies the proof for me if I do that. Okay, now what you'll see is that I put these angles on a unit circle. So notice that this point here has coordinates 1, 0. So we see that the radius of the circle is 1. The center of the circle is the origin, 0, 0. And therefore, every point here along the circle has coordinates the cosine of the angle, the sine of the angle. We've been using the unit circle specifically for multiples of 90. So we use this point, we use this point, we use this point, and so on. We haven't really talked much about the fact that the cosine of the angle is the x and the sine of the angle is the y, no matter where you are on the unit circle. So even if you're not at a multiple of 90, if you're at any point on the circle, the cosine is the x value and the sine is the y value. So you see, I've labeled this point cosine beta, sine beta, and I've labeled this point cosine alpha, sine alpha. Okay, now you notice the pink dotted line that I drew between these 2 points. My goal is to find that length. I'm going to call that length x. And we have 2 ways to do it. One of the ways to do it is to use the distance formula. Now, you might not remember the distance formula. It's probably been a while. You probably used it in geometry. It's based on the Pythagorean theorem, and I'm not going to prove it right now, but basically we have the distance x is equal to the square root of the difference in the x values squared plus the difference in the y values squared. So our x values are cosine alpha and cosine beta. So we have cosine alpha minus cosine beta. And the y values are sine alpha, sine beta. So we have sine alpha minus sine beta. Now I could write this in the other order. I could write cosine beta minus cosine alpha. I could write sine beta minus sine alpha. Because we're squaring, it doesn't matter what order we write that in. Now, to simplify this equation a little bit, I'm going to square both sides. So the distance squared is cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. Okay. Now, I had forgotten the order that I had written them in. For this slide, you'll notice I have them in the opposite order, but that's okay. As I said before, it doesn't matter. So here's where we left off. And what I'm going to do is a bunch of steps that change how this right side of the equation looks. So the first step you'll see is that I realize that cosine beta minus cosine alpha quantity squared means the same thing as cosine beta minus cosine alpha times cosine beta minus cosine alpha. Squaring is multiplying something by itself. And similarly, sine alpha minus sine beta quantity squared means sine alpha minus sine beta times sine alpha minus sine beta. In the next step, what I do is I use the FOIL technique to multiply these together. So the first gives us cosine squared beta. The outside gives us cosine alpha cosine beta, and the inside gives us cosine alpha cosine beta. So together that's minus 2 cosine alpha cosine beta, and the last gives us plus cosine squared alpha. And then we do the same thing with the other part. First, outside, inside, last, and we end up with this. Okay, what I noticed looking at that last step is that we have cosine squared alpha plus sine squared alpha. And remember, that is one of our identities, one of our Pythagorean identities. Sine squared alpha plus cosine squared alpha is 1. And notice that we also have above cosine squared beta plus sine squared beta, and that's the same thing. Cosine squared beta plus sine squared beta is also 1. So what I've done in the next step is just substitute 1 for each of those. And then in the last step, I added 1 and 1 and got 2. Yay! Hope you're following that step okay. Okay, so where does that leave us? There wasn't really anything else we could do to simplify it. So what I'm going to do now is repeat the process of finding the length x, but do it in a different way. So do you notice that we have a triangle right here? And we know the included angle, and we know this side length, it's 1 because it's a unit circle, and this side length, it's 1 because it's a unit circle. So we can use the law of cosines to get our third side. So that third side that I'm calling x, if we square it, it will equal 1 squared plus 1 squared minus 2 times 1 times 1 times the cosine of the angle in between. And this angle in between is the difference between this whole angle alpha and this little angle beta. So the angle in between is alpha minus beta. We can simplify this, and x squared equals 1 squared is 1, 1 squared is 1, 1 plus 1 is 2, minus 2 times 1 is 2. So 2 minus 2 cosine of alpha minus beta is another way to express the square of that length. So we have two expressions for the square of length x, and what we're going to do is set them equal to each other. So it looks like that. Notice that on both sides of the equation there's a 2. So all I did here was subtract 2 from both sides, and notice that every single term is a multiple of negative 2. So all I did was divide both sides of the equation by negative 2. And this is as simple as it gets, folks. So this is our identity, which tells us what to do if we have the cosine of one angle minus another. Okay, so the follow-up question is, now that we know that, what if we have the cosine of one angle plus another, the cosine of alpha plus beta, rather than the cosine of alpha minus beta? Well, fortunately, we don't have to go all the way back to the beginning and start from scratch like we did with the other one. We can take advantage of the use of some of the other identities we know. So what I've done is I've rewritten cosine of alpha plus beta as cosine of alpha minus negative beta, because minus negative is plus. Okay, so what we have in the previous line is we have cosine of one angle minus another angle. And that can be applied to this identity we just learned. So the cosine of one angle minus another angle is the cosine of the first times the cosine of the second plus the sine of the first times the sine of the second. Now there's another thing we know because we learned odd and even identities earlier in the chapter. We know that cosine is an even identity, so the cosine of an angle equals the cosine of the opposite of the angle. So the cosine of the opposite of beta is equal to the cosine of beta. And we also know that the sine of an angle is equal to the opposite of the sine of the opposite angle, or you could say the opposite of the sine of x equals the sine of the opposite of x. So that means that the sine of the opposite of beta is equal to the opposite of the sine of beta. So based on those, we can substitute, and we end up with this. And that's going to give us our second identity. So we have our cosine alpha plus beta identity for the sum of angles, and our cosine of alpha minus beta identity for the difference of angles. So let's end this video here, and then I'll make a second video that explains how we get the sine of alpha plus beta and the sine of alpha minus beta, as well as tangent. Thanks, guys.